Welcome, my friends. Lab number 9, calorimetry, dealing with calories. So what do we have? We're going to do three things in this lab today. Number 1, we'll determine the specific heat capacity of water. How much energy does it take to raise 1 gram of water by 1 degree centigrade? That's the specific heat capacity. As you know, water is unusual in that it has a very high specific heat capacity compared to many of these equal-sized molecules. That's why it's used for cooling purposes. So how are we going to do this? Well, we're going to do it electrically, at least for the specific heat capacity of water. What does that mean? We are going to input a known amount of energy into a known mass of water and measure the temperature change. And with that, we can calculate the specific heat capacity of water. So what I have here is 40.2 grams of water. 40.200 grams of water. The amount doesn't matter as long as you know what the mass is. Now, what we have here is a heater head. This is connected to a DC power source. So it'll tell us the voltage, as indicated in the pre-lab video. Voltage is joules per coulomb. It'll measure the current. The current is coulombs per second. And if we can measure the time, then with that we can multiply the voltage, the current, and the time in seconds, and that'll give us the energy input. And so the data logger serves as our count of time and also a count of temperature. So I've set it up so it measures 2 decimal places. So well, I'll have my camera person come here and then we'll get started. So essentially, if you look here, that's the heating coil. That's the coil that inputs the energy. We'll make sure it's properly inserted into the water, not interfering with the stirrer. We'll also make sure the temperature sensor is appropriately in there. All right. And then I'll turn this, let me start. I'll turn this on here. Oh, it's not plugged in. Can you pause? Sir, there we go. All right, it wasn't plugged in, so here we go. We got plugged in. So I turn this on, and you'll see it says here that systems are not ideal. By showing a red light. So basically in a separate container here, I need to set the things right. That indicator right on the top LED should not be on. All right, just a little twizzle brought it down. The light is off. So this says 2.6 volts and 2.10 amps. I'll put it back in my solution, in my measurement system. So that's our baseline temperature versus time. I'll now turn this on. And what you will see here is that the temperature begins to rise in a nice linear fashion. You can calculate our input energy by taking the voltage, the time times 1 second. That will give us watts or joules per second. So the idea is that we'll let it go here for a while. Let's see, maybe another 20 seconds. How about that? What I'll now do is I'll turn the power off, the heating off. You should be able to see that now the temperature level's off. And at this point I'll stop it. And so we want to get the coordinates of 2 points in the steep region. So all I have to do is scroll back. Doesn't matter what point I pick, but best to pick a point way up there. And with that we can read the X and Y, the time and the temperature. And then we can scroll way down further here. Doesn't matter where, so I'll stop somewhere there. And again, read the time and the temperature. With those 2 coordinates, the difference in the Y values is the temperature change. The difference in the X values is the time. And with that, and the mass of the water, and the voltage and the current, I'll turn it off, we can actually determine the specific heat capacity of the water. So I have this data in the Excel sheet, so no need to record anything. All that data is in the Excel sheet ready for you to use. So that's how we determine the specific heat capacity of water. If you are doing it in lab yourselves, I would have you do this a minimum of 3 times. All right, moving on now to the specific heat capacity of the aluminum. So I have in here an aluminum piece that I've put in boiling water in a test tube. So over time then, the system should come to equilibrium, and I'm at this point measuring the temperature of the water, and we'll assume in this case it's touching base there. So let's record this is 99.6 degrees for the temperature of the water. The sensor is hitting the bottom, and so that's why it goes over 100. But anyway, so we record the temperature of the boiling water. What's important about that? The temperature of the boiling water is equal to the initial temperature of the metal. In here, I have the styrofoam cup with a stir bar. I have 50 grams of water. I'll now switch here. And of course, in real life, we give you these directions. Press home, press F1 to get into graph mode. And then there are 2 of these temperature sensors. Make sure you're viewing the normal one. The big temperature sensor was around 100. This is a low one. So I'll just stop this by pressing play, start it again. Press F1 twice to kind of increase the sensitivity. I will now then transfer the metal into the water. And as you might guess, the temperature goes up. And so essentially then you wait until the system comes to stable values. Let's assume that that's a stable value. I press play to stop. I can then record the temperature. We're only interested in the temperature. That's T final. But here's the important point. It's T final of the water, but it's also T final of the metal, because the 2 come to temperature equilibrium. How about T initial of the water? T initial of the water, scroll down, read at the baseline there, read that temperature at the baseline, and then with that you know the initial temperature of the water. And so with this, temperature of the metal, starting initial around 100, final is the final for the water here, and we have the temperature initial of the water. With those then in the equations provided, one can calculate the specific heat capacity of aluminum. So in terms of expected values, you expect 0.9 joules per gram per degree centigrade for aluminum. You expect about 4.2 for the specific heat capacity of water. But you guys know that already. All right, last part. What's the last part? Enthalpy of fusion of water. Fusion is the fancy term for melting. So let me switch here. $80 grams of water, non-mass, about 80. Start recording the temperature. F1 to sensitize. That's the temperature of the water. Go down to your freezer, which I did. Get a piece of ice. Measure the temperature of the freezer. Works out to be around minus 15 degrees centigrade. Get the exact value. In our case, you actually go to the freezer and get the value. We won't be doing that here. Quickly take out a block of ice. This one is kind of begun to melt already. All right. Measure the mass of the ice. Measure the mass of the ice. Put it in. Temperature, of course, goes down. And we're gonna wait until the whole thing is melted. And since it will take a little while, we'll let it go while I describe certain things. So what's happening here? We have a known mass of ice that starts at a certain temperature. It warms up to 0 degrees centigrade. Then it melts. That melting is isothermal, occurs at the same temperature, 0 degrees centigrade. After it's completely melted, then that water that came from the ice, and at this point we distinguish from the 80 grams we put in, raises in temperature with the rest of the water to a final temperature. So in this case, the system is the ice. So what happens to the ice and its water that comes from the ice? It goes from minus 15 to 0, 0 to 0 for the melting process, and that's where our enthalpy of fusion comes from, and 0 to the final temperature. What happens to the water? The water has an initial temperature. Okay, we're differentiating this water from the water that came from the ice. So this water starts at the initial temperature and drops down to a final temperature. As you can see here, we're still going down. And so we'll pause here for a little while. All right, so we'll suppose here that it's melted, and physically you can look into the styrofoam and verify that there is nothing floating on top. Of course, ice is less dense than water, which happens to actually be a beautiful thing. But anyway, and so we can record the final temperature. This is the final temperature of the water. That was water before. It's the final temperature of the water. That was ice, then melted, and then joined the other water. And so T final is the same. So if I stop here, we could read then the temperature of our T final. And we can go back, scroll back, and read the temperature of the water. That was water before we dropped in the ice. So again, that's our lamp. All these values, just to make life easier for you. I collected the data. It's hard to collect the data from this. And I didn't want to repeat it 3 times. Anyway, so I put in the data in the Excel sheet. And so what I just wanted to do here is certainly give you a visual of how the actual experiment is done. See you in lab number 10, my good friends. Bye-bye.